Hey, I'm Mark, and I'm the captain and electrical engineer of Team Orion, which makes soccer robots. I'm most proud of the bottom PCB on these two robots.
The main components are the step-down converter, reflective sensors for measuring the color and distance, the boost converter, and the high-voltage control system. I used calculations from an MIT team paper to determine the voltage and capacitance needed for the solenoid to kick the ball to the power limit. However, the kicker strength was somehow too weak. After debugging and many iterations, I decided to increase the voltage. So I implemented a voltage doubler into the boost circuit, achieving 100 volts, which easily reached the power limit. To prevent the supply voltage from dropping when the solenoid is fired, I used optocouplers and MOSFETs to disconnect the solenoid and capacitor from the rest of the robot when firing. On the software side, I implemented an equation that generated the optimal path the robot should take given the ball's direction and distance. With the software engineer, I also implemented wireless communication for offense and defense switching that was key in winning the Best Video Award at the Virtual 2021 World Cup. For 2022, I'm designing a custom brushless motor control board. Creating a three-phase AC signal depending on the rotor position and digital inputs from the Teensy was a challenge, especially with the chip shortage. To adapt to the chip shortage, I learned to streamline the assembly process using a hot plate and stencil, enabling me to solder QFN packages that have pads underneath the IC. On the same shelf, I keep my self-driving RC car. The idea was to create a cheap alternative to 360 LiDAR. I made Python scripts to extract, filter, and mirror the data from the RealSense D435. I used the semantic segmentation convolutional network. An RGB image would go in, and a depth image would come out. I decided to upsample via deconvolution. The end experiment shows me pushing chairs over. The darker the area, the closer the object. The low frame rate is because the network was running on a Raspberry Pi, and I couldn't quantize or train the network for speed improvements. The low frame rate forces the bit-by-bit movement of the car, but to my surprise, it even works outside where it was not trained at all. Given the difficulty and time crunch, I'm extremely proud of the progress I made.
I hope to continue making awesome projects at MIT.